So students, today we will continue with our chapter on the magnetic effects of electric current. Yesterday we learned the right hand thumb rule that gives you the relation between the magnetic field that is produced in a current carrying straight conductor and the direction of current. I repeat once again, the right hand thumb rule gives you the relation between the direction of current flowing in a straight conductor and the direction of the magnetic field that is produced due to the current flowing in this straight conductor. Right? If you have seen, just to revise, imagine you are having a current carrying conductor held in your right hand with the thumb stretched along the length. This is the length. So if the direction of the thumb gives the direction of the electric current, then the direction of the curled fingers, this is the direction of the curled finger, so the direction of the curled fingers will give you the direction of the magnetic field that is produced around the conductor. Right? Now students, today we will take up this. Before that, please remember that the right hand thumb rule is also called the Maxwell's screw and cork rule. Right? You remember when you must have opened a bottle, right? So when you're turning the bottle, the direction in which you are turning that cap, the cap of the bottle, that direction gives the direction of the magnetic field. And when you're turning it, if it goes down, then that is the direction of the currents. When you're opening it, then the cork comes on top, that is the direction of current. That is actually Maxwell screw cork rule. I will write it and send it across to you during an assignment. Now students, today we are going to take up what is known as the current carrying circular loop and the magnetic field. So today we will be talking about the magnetic field produced by a current carrying circular loop. Right? Now what has to be done basically is we will study the pattern of the magnetic lines of force that are produced by this current carrying circular loop. Right? For that, what you have to do is you have to take a cardboard, a big cardboard, right? And there will be two holes in the cardboard. Then you take a 3 meter long insulated thick copper wire and form a loop by passing the copper wire through the two holes of the cardboard. You can form one loop or you can form a number of turns also. Keep on turning it, and then what you have to do is connect the two ends of the wire. One, you can connect it to a rheostat. The rheostat is meant to increase or decrease the flow of current in order to study the intensity of magnetic field. Then also in series you will connect a battery, that is a number of cells, and then you will also connect a plug key. Now students, with the help of the same iron filings, you can place the iron filings at the two positions on the cardboard where the loops are passing. So near the two points where the loops are passing through the cardboard, you can place iron filings on that, and you will notice once you switch on the current and tap the cardboard, you will find that the iron filings will arrange themselves in the form of concentric circles. Right? You saw the current carrying straight conductor, right? The same concentric circles will be formed at both the points where the loop is passing through the cardboard. Right? Now students, here also you will find that the magnetic lines of force of a current carrying circular loop, right? The magnetic lines of force of the current carrying circular loop are also in the form of concentric circles. But there are a few observations that you have to make, students, over here. You will see very clearly that as you go away from the loop, the circles, distance between the concentric circles keep on increasing. Right? So you look at both the loops, as you go away from the circle, the distance between the concentric circles keep on increasing. That is because the intensity or the strength of the magnetic field decreases as you go away from the conductor. Now students, one very interesting thing you will also see, that as you go towards the center, means as you move away from the loop and come towards the center of the loop, right, you will find that the circle ultimately becomes a straight line with one side as the north pole, the other as the south pole. So as you go towards the center of the loop, the circles become bigger and bigger, and ultimately they become a straight line. Now students, supposing you have only 2 turns of copper wire, as you increase the number of turns, that means if the number of turns are increased by n, then the intensity of the magnetic field will also increase n times. N times means how many times you increase the number of turns, by that many times the intensity of the magnetic field produced in the loop will be the same. Now students, remember, you are seeing these concentric circles only at the points P and Q where the cardboard or the copper wire is touching the cardboard. But please remember, on every point along that circular loop, you will find that they are in the form of concentric circles. These magnetic lines of force, that is the concentric circles, magnetic lines of force, are present at every point on the loop, right? Not only at the point where the wire is touching the cardboard. So kindly remember that at every point on the circular loop, you will have these magnetic lines of force in the form of concentric circles, right? Now students, I believe you have understood the magnetic field lines produced by a current carrying circular loop. You only have to remember the important things that you have to remember is that what is that circular loop. Then you have to remember that the magnetic lines of force of a current carrying circular loop are in the form of concentric circles, and these circles become bigger and bigger, or the distance between them increases as we move away from the loop, and towards the center of the loop the circle becomes a straight line with one end as the north pole, the other end as the south pole. Students, if you increase the current by increasing the number of cells also in this loop, the intensity of magnetic field will be stronger, right? So this is very, very important. Then students, as you increase the number of turns also of the circular loop, you will find that the intensity of the magnetic field will increase, and that can be studied from the number of circles or the crowding of the circles that will take place. What are those circles? They are basically formed by the iron filings which are kept on that cardboard, and the lines along which those iron filings arrange themselves are in the form of concentric circles, which represent the magnetic field produced because of that circular loop, right? Now students, if you increase the current, the circular loop will come closer because the strength of the magnetic field or intensity will be stronger, and if you decrease the current with the help of the rheostat, the magnetic lines of force of those concentric circles will move apart from one another, right? Then if you increase the number of turns, the magnetic field will also increase. So this is all about the magnetic lines of force produced by a current carrying circular loop. Now students, we will talk about something which is called a solenoid. A solenoid, right? Now what is this solenoid? If you look at the diagram of the solenoid, right, it is very similar to that of a spring, right? So what is a solenoid? You'll have to define. Now this spring-like structure that you are seeing is actually made up of insulated thick copper wire which is wound in the form of a coil, right? Cylindrical coil like a spring. You can take it like a big spring. You have seen some shock absorbers on the motorcycle in the form of a big spring, so that would be the shape of a solenoid. So a solenoid is many turns of insulated copper wire. You can prepare it by winding it around a cylinder, only you should see that the adjacent turns do not touch one another. So a solenoid is a coil made up of many circular turns of insulated copper wire wound in the form of a cylinder and resembling a spring, right? Now students, if you connect the ends of this solenoid to a source of current with like a battery, then when current is passing through this solenoid, when current passes through the solenoid, you will find that a magnetic field is going to be generated. That you can easily confirm it by placing maybe a magnetic compass needle. You will find that the magnetic compass needle starts deflecting, showing you the presence of magnetic field. Now what is important about this solenoid is you will observe that the magnetic lines of force of this solenoid are very similar to the magnetic lines of force of a bar magnet, right? So the bar magnet, you will find the magnetic lines of force are in the form of closed curves starting from the north pole to the south pole. So in the solenoid also, the properties of the magnetic lines of force of a solenoid are very similar to the properties of the magnetic lines of force of a bar magnet. What are the properties? You will find that these magnetic lines of force, they will start on the north pole, end on the south pole. These magnetic lines of force will be parallel to each other, they will never intersect each other. Then these magnetic lines of force are more crowded near the solenoid and less crowded as you move away from the solenoid. These are some of the properties of magnetic lines of force of a solenoid and a bar magnet, because both of them have similar magnetic lines of force. You look at the magnetic lines of force of a bar magnet maybe in your last year's textbook. These are the same magnetic lines of force that is there in the solenoid. So that means a solenoid acts like a bar magnet whenever a current is passed through it, with one open end of the solenoid behaving as the north pole, the other open end of the solenoid behaving as a south pole. If you see at the center of the solenoid, the magnetic lines of force are they are completely parallel to one another. What does this parallel magnetic lines of force tell us? These parallel magnetic lines of force tell us that within the solenoid, the magnetic field is uniform. Now students, in the solenoid also, if you increase the number of turns, the intensity of magnetic field produced at the center of the solenoid, you are the solenoid, na? So at the center of the solenoid, the magnetic lines of force will be stronger as you increase the electric current flowing through it, right? So even if the number of turns are increased, the magnetic lines of force will increase. If you increase the current flowing through that solenoid, the magnetic lines of force inside, or the intensity of the magnetic field inside the solenoid will increase. Now students, in your textbook it is not exactly written, but within the syllabus of last year it was mentioned a very important application of a solenoid. The most important application of a solenoid is making or manufacturing permanent magnets from suitable materials like tungsten, cobalt and etc. So if you take a suitable material, a piece of a material, and put it in the hollow of that solenoid, if you keep it for some time and you pass a strong current, because of the strong current a strong magnetic field will be produced and you will get a permanent magnet from that piece of tungsten or cobalt or carbon steel or whatever, right? So you can prepare permanent magnets by using a solenoid. There are two materials you probably must have learnt last year, nipper mag and alnico. Nipper mag, that is a alloy, right? And alnico. Alnico is an alloy of aluminium, nickel and cobalt, and nipper mag is an alloy of nickel, iron, titanium and aluminium, right? So since it is not there in your syllabus, you need not worry about it. This I provided it to you as an extra information on the applications of a solenoid, right? So students, today we have learned about the magnetic lines of force of a current carrying circular loop. We also studied the magnetic lines of force of a solenoid. What is a solenoid? A coil of insulated copper wire wound in the form of a circular loop, but in a cylindrical form. I repeat once again, many turns of insulated copper wire wound in the form of a cylindrical spring is called a solenoid, right? So we have now learnt about a solenoid in detail. Now in the next lecture we will be taking up another aspect of the magnetic effect of electric current. We will see how if a current carrying conductor is placed in the magnetic field of another magnet, like supposing this is a current carrying conductor and I place this current carrying conductor within the magnetic field of a horseshoe magnet, then this current carrying conductor will start getting displaced, right? So this is how we will learn about the magnetic effects of current in our next concluding lecture. Till then, students, take care, stay safe, and goodbye to all of you.